Hello everyone, hope you're doing well. And as always, if you are new to my channel, I would humbly request you to subscribe to my channel so that you'll be able to see all the latest engineering videos that I will make for you. Thanks. So today the problem at our hand is we want to do an FE analysis of this cantilever beam. This is an aluminum beam and it's basically a 6061T6 aluminum alloy rectangular beam. And in this beam, we have a vertical force of 150 kilonewton being applied at the tip of this beam, and the length of the beam is 1 meter with a cross section of 100 mm by 300 mm. And if you look at it more clearly, you will see that for this beam, this is our beam aluminum 6061T6. This is the aluminum beam material, and its modulus of elasticity is 68.9 gigapascal, and its modulus of uh, rigidity, which is given as 26 gigapascal. The yield strength of the material is basically 255 megapascal, and the ultimate UPS of this material is 290 gigapascal with the Poisson's ratio of 0.35. Okay, so let's start doing this problem. As we already know, the geometry of this beam has been explained to you, the material properties being told. So if you look at it, first of all, what we're going to do is we're going to select the preferences for the material, the structural, okay. Then we'll go for the element type and we'll go add, edit, delete, and add. You will see all these element types for different types of structural elements. We'll say beam and we'll select the two noded 188 element for us. We'll say OK. We will close. Once this is done, we do not have any real constants for this elements. So we'll go for the material properties. And for the material properties, then we go to material models. We go the material models, which is structural, linear, elastic, and we go for the isotropic. And here we're going to know that our modulus of elasticity is 69 giga. It's basically it's 69 E9, and the Poisson's ratio is 0.35. Okay, so this is what it is. Once this has been done, we can basically go out of it. And now we have to select a section. When we go to selection, we know we're going to go section library. And now we're going to go to the beam and we go to the common sections. If you look, we have all these different types of sections. Over here, you can see a list of various types of sections, almost the channel section, the I section, the L section, the Z section. Okay, and these subsections are also there. Okay, so we have been given over here this section, and we will go and select this section. We will say here is basically it's and we're going to say it's not, and we're going to apply here. Okay, once this has been done, we close it up, and then we go for the modeling. How to model this over here. And for model, we're going to go for create, and here we're going to do is key points in active coordinate system. The first key point, basically it's a 1 meter beam, and we will say that its value at the origin will be 0. Okay, and this is the key point numbers. Okay, we'll go for apply. Then we go to the second part, which is key point number 2, and the length of the beam from 0 will be 1 meter. So we'll put 1 here. These are our coordinates x, y, and z. So it's basically original point was 0, and we move a distance along xl 1 meter, and we give it the value. Once we can apply and say Okay. You can see there are two key points being generated, 1, 2. Once this is being done, we can go to lines and we will say we draw straight lines from here to here and we say it's being applied. And once this has been done, now what we're going to do is basically the model has been done. So now we go to meshing, and in meshing we're going to divide into small elements. So we will say that the option number, there are many options. We'll go to size controls, manual size, global, then size. Here we have two options. We have size element, edge length of the element, and number of element divisions. Okay, we will select this option for size element edge length, and we will say it has 0.045, 0.045. This is an element led selection. We're dividing the elements into small edges, and we'll say it as OK. Once this has been done, we'll basically go for the meshing. In the meshing, we need to say meshing for key points. We'll go to mesh lines and we will select this and we'll say recall, and we're going to basically close it here and then we'll close it here. So once this is being done, we can say plot and check whether the elements have been created. We'll see yes, the element is being created. Once this has been done, this is basically the also part of, these are all parts of pre-processing phases. Then after meshing, we'll go and we'll apply the loads, and we'll apply the loads, define loads, apply structural structural constraints, displacements on the, we'll see it will be the displacements on the key points. Left side is the fixed support, so we'll go here and we'll say all degrees of freedom, and we can say we want 0, and we will say there are many other constraints, ux, uy, uz, displacement along x, displacement y, displacement along z, rotation about x, rotation about y, rotation about z. So there are 6 of them. As you know, there are 6 constraints for a normal system, 6 degrees of freedom. They are basically. So once it's been done, we're going to say it as OK. See, yes, OK. You can see the constraints are being generated over here. So once it's been done, now we're going to apply the force. Okay, we're going to basically be applying the force. If you look at it, the force is 150 kilonewton. So this is going to be the force applied on the key points. This is our key point, and we'll apply the force. So we have forces fx, fy, fz, mx, my, and mz. We need to apply the force along the y-axis. So it's the y-axis, and we'll write it as minus 150 E3. And you can see this is y, but this is positive y upward. The applied force is going to downward. So let's see applied. Yes, you can see this is the force being applied at the bottom in the negative of the y-axis. Now once this has been done, the entire pre-processing phase has been completed. So this has been done now. We have to go for the other phase, which is the solution phase. So we will apply the solution phase, and once this has been done, we'll say that solve the system for us. The current LS means the current load steps that are being applied in the pre-processing. So now we're going to say it OK and see whether the process has been completed. The software says solution is done or not. So the software is saying us that it's being solved. So you can see the solutions and all these outputs have been generated. Now the solution phase has been completed. We can close it down, and now we're going to go for the result phase. So we will say plot, replot. In results, we can see all the various types of results that will be generated. We will say and ask the software to plot the results. We will say deformed shapes and undeformed. We will say deformed plus undeformed. See what does the software says to us. And see, this is the deformed shape of the cantilever beam. And you can see the deflection is 0.003452 of a meter. So in millimeter, if you look at it, it's 3.452 millimeter, and meter it's 0.003452 of a meter, which is, I think, acceptable. Then, so once this is being done, we can basically, after seeing this, we can go to other things. We can say the plot results, and we can see go for the contour plots. And if you look in the contour plots, we have many options, but we will go for the nodal solutions of the contour plot, and we can see that this is the nodal solutions degree of okay over here, and we can say the y component of displacement over here will be shown to us. If you look at it, this is the y component of displacement, and being shown to us. Then we can say that we can also go for the displacement vector sum. This is the vector sum for displacement of x, y, and z. It's giving us this result. And we can also see over here by seeing the rotations, the displacements, because the force will movement and movement will generate rotations. So we can say the rotation vector sum over here. These are the rotation vector sums, and you can see the rotation is basically generated here is 0.004. This is the value 0.004831. This is our value for the rotation 0.004831, and certainly this will be in the radians. Okay, so this value has been also been found. Okay, then if you want, we can also go to the elemental solutions of this, and we can basically see the structural moments over here. If you go, structural moments generated as a result of this z component of the moment. This is the structural moments being generated of a system, and then basically we can also go to list results, and we will see the list results. We can go to the nodal solutions. All these results will be seen. Like the nodal solutions, we can say that this is the displacement vector sum. You can see these are the results being generated on the nodes of the system that have been there for the whole displacement in x, which is very small displacement in y, and displacement in z. This is the u sum, no displacement in x, no displacement in z. This is the displacements in the y-axis. You can see from the force applied, the displacement will be along the y. Then we can also go for the rotation vector sum if you want. Here, this is the rotation vector sum, and you can see these are the rotations about x-axis, rotation about y-axis, and this is the rotation about the z-axis. You can see the rotation about the x and y-axis is almost zero. Okay, and the rotation about the z, this is the main prevalent of among all the three. Rotation about the z-axis of this cantilever beam. You can use this in your report if you want to print out. Once this has been done, now we can basically see what will be the shear forces and bending moment diagrams generated for this system. So for this, if you look, we can basically go for here, and we'll try to go for the element table here. If you look, we go for the element table, and we can define the table, and these are the call signs for generation of the shear force, bending moment, the bending stresses that you are required for your project. And if you go here, you can see a lot of different call signs that you can generate for this from ANSYS. Okay, you will go in the last and you say by sequence number, and you will write the first sequence number as 6, and you will apply here. Then you again go for the call sign, and you go and you apply 90. These are the call signs of the elements that you must learn in order to apply it and get the results output for shear force and bending moment and bending stress of your beam. Okay, you can see on the left they have been coming. Then you again apply for the, then again just to let you know that these call signs, the first two ones, 6 and 19 call signs, are basically for the shear force diagram. Okay, they are the shear force diagram, and basically they are about the y-axis, the shear force. Okay, remember 6 and 19 are for the shear forces. Then you will again go and you'll be interested in the bending stresses of your uh, beam. So now for the bending stresses, you'll be applying it as 3, and then you can again go and you can see you'll be applying for the uh, another one, which is basically the 16. Then you will go again for that, and you will basically ask for the bending stresses. Best bending stresses. But let you know, this 3 and 16 are the bending for the bending moment about the z-axis. Okay, so this is we done. Now we shall be interested in the bending stresses about the y-axis. So you can say the call signs for them are 32. We apply them, and then again go for the uh, this, and we'll ask for the 37, the bending stresses, and you can close it down. Once this has been done, you can close it. Now, once this has been done, you can basically close it up here, and you can go in the plot results, and you will go the line element results. Okay, you can say just simplify its plot elements and go for the line element results. And you know here this is for the first, it's a node I, and this is the second node. So remember that 6 and 19 were for the shear force diagram. 6 and 19 were for the shear force diagram. And all right, this is our shear force diagram. If you want to see your respective bending moment diagram, remember it was 3 and 16. Let's start with that. So this is your bending moment diagram being generated. And if you want your bending stresses, it will be 32 at node I and at 37 at the node J. 32 and 37 node J, you can basically see these are the bending stresses being generated of the structure. So once this has been done, we'll write it as plot the elements. Now this has been done. Okay. Now what we'll do is basically we're going to plot control, span, zoom, rotate, and we'll try to make this beam into an isometric uh, basically view. Now once this has been done, what we will do is we go to plot controls, and we'll go style, and we'll go to size and the shape, and we'll say on, and you can see your beam has been come into the real one, the real on beam. Okay, so once this has been done, this is the more realistic way over here to see. So here you can see a lot of results to be seen over here. I can always go to the contour plots, and we'll say the element solutions, and you can see a lot of stresses and everything over here. You can see uh, this beam, and you can see the first of all, if you go deform shape and of this beam, you can see this is the deformed shape of the beam. And here, if you want to, you can see then basically make a better version of it, and you can see the deform shape in an animated way, and deform plus and deform will be a better option. And you can see how the load is being affecting it and deforming the beam for us. So this is the version, and we can basically stop it, and then we can also close it down. We will say plot, or you can say replot it. Okay. Now we can go to the contour plot, and you can see a lot of contour plot, and you can see these are the x components of the stresses, and we can go for the other ones if you want. We can go for the shear stress of this beam if you want. This is the shear stresses. These are the results being generated as a result of the shear stresses. You can also see the principal stresses. It's a very first principal stress of this beam. This is the first principal stress. And if you want, you can see the third principal stress also. Okay, these are the most the third principal stresses being generated. And if you want, you can also see the most important one, which is the von Mises. These are the von Mises stress, and if you look at it very clearly, this value is basically at the is coming out to be 97.8, 97 e to the power, it's 0.97 e to the power 8, so it is 97 megapascal. You can say it 97.8 megapascal. So if you basically go to the tables of your RC Hillner, and you can see this is our aluminum alloy 60626, and if you look, the yield strength of our alloy is 255 megapascal. 255 megapascal. And what is ANSYS giving us? If you look at it, our value of the von Mises is 97.8 megapascal, which means our structure, when this loading is applied, is basically safe. So this is being telling us that everything is okay as far as the structure is concerned. Okay, then you can basically get all the different kinds of results over here if you want to. That we're performing different results. So another thing is that you can basically, apart from this, you can make your own report out of it if you want to. And just one thing, you can also, if you want, you can basically capture image of this also for your report also. If you want, I can, this is basically your file which has generated an image. You can always file, save as on your desktop. You can print it, and this will be saved in your report. Okay, but remember, this black zone is very much going to take a toner. Okay, so if you are wise enough, you can use another option if you want to, and that option is basically going to say you if you go here over here, write to meta file, and you say invert white black. If you do it this, you can see this is file 00. You can say file 134. If you see, this is file 134, and if you go to your desktop and you save this meta file over here, file 134, you can see this is if you go, it's file 134 is somewhere here. This is one of our files that I've saved. If you look, this is the file 00. You can see it's very clear image, and the white background, and this image is coming at the front of you. It will save your toner, and it will be a better option instead of, otherwise a lot of ink will be used. Okay, so this is just to help you around as far as your report is concerned. Okay, so this thing, another option that you can do in ANSYS is basically you can generate your own report over here. That will be very well for you. Report generator. Here is a report generator, and if you look at it, you can create, choose basically make your own report over here. Okay, and you go okay, and here basically you can capture all the images that you want. You can say this is file image 1 if you want to. Okay, here it is. Then you can also basically uh, create, if you want, this is being done for you. And if you want further, if you want images to be done, you can basically select over here. You can basically capture your image over here. If you want, you can capture any deformed shape or deformed results. Here you can say stress, if you want to say XY shear stress, if you want to capture. Uh, you can say okay. This image will be basically stored over there. You can basically also, if you say, you can select any tables and nodes or something like that. It will be selected. And if you want, you can basically say matpop if you want. It will be selected. Okay, so in this way, once you select this, uh, you can basically go over here and this way you can insert any text over here as your choice. Okay, you can basically if you want to insert any text, you can report your heading over here. You can write your title as your CEP project. This is, let's review your name, 123, your subtitle, any of your ABC group, GRO. When you, it will be saved over here. Okay, like this, you can say. Then you can basically insert any of your images if you want to. You can insert this image, you can insert the another image, you can insert your tables, blah blah blah. You can do it, and once this has been done, you can basically preview your report will be generated. See, this is your report generated. You can just play around and learn more about it. This is the report, and these are your tables and everything over here. You can insert as much data you want. That is going to be optimum for your report. So this is how work is being done in ANSYS. And mind you, this is basically a what we have done here is basically a statically determinate beam. So we will like to do another complicate problem, and in another problem we will try to make the statically determinate beam into a statically indeterminate beam and see how ANSYS responds to that and what will be the values of the outcome of the deflections with the same force. Okay, so thank you very much, and you have a wonderful day, and thanks again.